Good morning, everyone. My name is Masahiro Tsujie. I'm also from Railway Technical Research Institute in Japan. Today, I will talk about a study on the initiation of head check of the low rail using multi-body dynamics. There are 5 points of my presentation. First, background and purpose of my presentation. Second, on-site investigation. Third, analysis of rail in service. Then, wheel and rail contact analysis at head check appearance site. Finally, the consideration of the initiation factors based on the wheel and rail contact analysis. Now, I would like to begin by providing some background information of my research. As you know, head check is one of the most famous cracks appeared on rail. In general, head check appears at the gauge corner of the high rail. But some head check appears at the rail surface of the low rail in several networks in Japan. At these sites, vertical box accelerance and wheel and rail noise become significant. Furthermore, ultrasonic flow detection cannot be carried out in these sections. However, the occurrence situation and the initiation factors of these cracks has not been clarified. So, the purpose of my presentation is to clarify the occurrence situation and the initiation factors of head check of the low rail. I will talk about the results of on-site investigation. We conducted the on-site investigation. The number of the site investigation is 50. First of all, we summarize the radii of the curvature where the head check of the low rail appeared. For comparison, the radii of the curvature where the head check appeared at high rail, as shown light figures. According to the left figures, head check of the low rail tend to appear in the curved section where the radii are from 400 to 600 meters. From the comparison between left and right figures, head check of the low rail seems to appear in the sharp curved sections. From the on-site investigation, head check was classified into 2 types. That is, continuous types and discontinuous type. About continuous type, the band of the contact surface of wheel and rail is not changed. On the other hand, as for the discontinuous type, the band of the contact surface has changed complexity. Especially, the contact band is wide. Where the contact band is wide, crack mouths gather density. As for the future of these cracks, tracing the surface of the head check in the direction of train running, it feels smooth. But in the opposite direction, it feels large. According to these conditions, the longitudinal creep force due to the wheel and rail contact affect the head check appearance. By the way, some cracks like head check were confirmed near the welded part. This type of crack appeared only near the welded part. Therefore, this type of cracks is the fatigue damage due to the rail surface irregularity on the welded part. Next, I would like to point out rail surface irregularity, as you can see this image here. So we measure the rail surface irregularity in these sections. Here shows the example of the measurement of rail surface irregularity. As shown in these figures, the rail surface irregularity has changed complexity. Here, the saturation point of the measurement results at every 25 millimeter interval is due to the rail joint. In order to obtain the features of this regularity, we calculated the power spectrum of rail surface regularity, which we measured. As shown in the right figures, the spectral frequency of 6.3 1 per meter was dominant. That is, the wavelength of the rail surface irregularity is approximately 160 millimeters. In order to grasp the features of head check, we conduct the cross-sectional observation. We conduct the cross-sectional observation to see the crack propagation and the plastic flow. Here shows the outlook of the analytical rail. The dotted line indicates the cutting position. Here shows the example of longitudinal. Here shows the example of the cross-sectional observation in longitudinal direction. As you can see, some cracks propagate opposite direction to the train running. Next, we conduct the cross-sectional observation to obtain the features of the plastic flow due to wheel and rail rolling contact. Here shows the observation results of the longitudinal direction and the transverse direction. It is confirmed that the plastic flow and the rail surface is observed both in the running direction and to the field corner side. Therefore, the plastic flow under the rail surface was confirmed in the rail for analysis, which has the head check on the rail surface as shown in this figure. According to the directions of plastic flow, it is thought that the longitudinal creep force affected the head check appearance. Next, I will talk about the wheel and rail contact analysis at the head check appearance site. The rail surface irregularity, where the discontinuous type of the head check appeared, is changed complicatedly. Therefore, we examine the contact conditions between wheel and rail in case of the vehicle running on the track, having a rail surface irregularity by use of SIMPAC. Here shows the outline of an analytical model. The area around the center of circular curved section, where the head check appears on the low rail surface, was modeled, and the rail surface irregularity of the model was set that the wavelength is 160 millimeters and the amplitude is 0.01 millimeters. Those of the irregularity is based on the results of the on-site investigations. Here shows the analytical results of the longitudinal creep force and the wheel load, the longitudinal creep ratio. According to these results, longitudinal creep force is fluctuating due to the rail surface irregularity as a result of the severe wheel and rail contact conditions. Actually, the plastic flow was observed at the field corner side at the concave section. Here is the plastic floor. Therefore, it is thought that contact conditions of the wheel and rail is severe at concave section compared with those before and after the convex sections. Next, I will talk about the consideration of the initiation factors of a head check on the low rail. We conducted the wheel and rail contact analysis by use of SIMPAC. According to the on-site investigation, all of the sites where head check appearance of low rail is tilting train operated. Therefore, we conducted wheel and rail contact analysis in case of tilting train and non-tilting train. Here shows the outline of the analytical model. The radii of the curvature is 600 meters, and the cant is 100 millimeter. However, the equilibrium cant is calculated as 185 millimeters. Sorry, I have a mistake. Running speed is not meter per hour, but kilometer per hour. Sorry. Very slowly. Therefore, this circular curved section is cant deficiency. Here shows the details of vehicle model on light table. These parameters are based on the actual vehicles in service, especially the value of the wheel diameters are different, these parameters. Here shows the analytical results of the longitudinal creep ratio and lateral force and the difference between the diameters at high and low rails. As for the tilting train, longitudinal creep ratio is more than for the non-tilting train. It is the result of the difference between the diameters at high and low rail due to the lateral force. Especially the difference between the diameters at high and low rail of tilting train affects the longitudinal creep ratio larger than that of non-tilting train because of the difference of the wheel diameter of both trains. In this slide, I will explain the previous analytical results in the figures. According to the previous analytical results, the lateral force generated by the tilting train is higher than that by the non-tilting train. The wheel axle moves towards the outside of the curve more in case of the tilting train than in case of the non-tilting train, resulting in more difference between the diameter of the wheel of the high rail and that on the low rail. Moreover, because the diameter of the wheel of the tilting train is smaller than that of the non-tilting train, the longitudinal creep ratio becomes larger in case of tilting train. Therefore, this longitudinal creep ratio resulted in the appearance of the head check of the low rail. The main findings of this study are as follows. Thank you very much for your kind attention.
Time.